about quantization symplectic varieties over the ring of integers and over other rings. The main result is due to Roman Travkin and its write-up, which is still very much in progress, is joined with Ekaterina Bogdanova, Dmitry Kubrak, and myself. Okay, so thank you very much for inviting me to speak here. So the setup is the following. So I will fix some scheme X over R equipped with a Poisson structure. So there are okay, thank you very much. Yeah, so so X is a Poisson scheme. So this is the bracket, Lie bracket on functions, which has a property that the commutator is a derivation with respect to usual multiplications on X. And so a quantization. So this is Poisson structure. Quantization of this Poisson scheme is a sheaf. We work with the risky topology at this moment, a sheaf or H of algebras over my base ring R over the power series in formal variable H over this ring R algebras together with an isomorphism. So if I mod it out by this sheaf of associative, so this algebra is assumed to be associative, but not necessarily commutative. And if I mod it out by H, it comes together with an isomorphism with the structure sheaf. So such that the following conditions are satisfied. Well, first of all, ORH is flat over the ring of power series and complete, H adic complete. And secondly, so now I have to explain how it's related to this Poisson structure. So let's consider the composition. So if I have an element A here, I will denote by A bar the corresponding function. And then the relation is that the condition is that for any A and B in OH, A times B minus B times A, the commutator in this associative algebra, well, it must be 0 modulo H. So because OH is flat, it's uniquely divisible by H. And the condition is that this is the Poisson bracket of A bar and B bar plus modulo H squared. Okay. So one can check that quantization of an affine variety is the same thing as quantization of the algebra of its global functions. And so here is the basic example of quantization So we can consider for X the cotangent bundle, the total space of the cotangent bundle to some smooth variety Y. So this has a projection to Y, which I will denote by pi. And so Y over R is smooth. So then this has the cotangent bundle to any variety has even a symplectic structure. So there is an exact symplectic form d eta. It's a two form on X, and it defines in particular, it gives me it's non-degenerate, so it gives me an isomorphism between the cotangent bundle to X and the tangent bundle. And if I have a differential form df, I will denote the corresponding vector field, which is called the Hamiltonian vector field, by hf. And then the associated Poisson bracket is defined by the formula. So the commutator is the derivative of G with respect to this Hamiltonian vector field. Now, in this case, there is a natural quantization of this symplectic of this Poisson variety, which is given by differential operators on Y. So the differential operators is a sheaf on Y. It's a sheaf of associative algebras. It's a filtered sheaf. There is a filtration given by the order, and then can apply the Riesz construction to construct a deformation of this associative algebra to its associated graded algebra, which is the symmetric algebra of the tangent sheaf. So it works as follows. So you consider power series in differential operators with power series with coefficients in differential operators, and here you consider the subalgebra d by h, which is called asymptotic differential operators, and it is generated by functions and h times vector fields on Y. Okay, so so this is still a sheaf of algebras on Y, and it has the property that if you mod it out by H, then you get the commutative algebra, symmetric algebra of the tangent sheaf. So now, as I explained, given in the affine case, given a quantization of a variety is the same thing as given quantization of the algebra of global functions. So this general fact allows to localize dyh over X. So I will. So there is it gives rise to a quantization with the property that its sections over pullback of an open subset of Y is this algebra of asymptotic differential operators, global sections over. Okay, so in this property uniquely determines for sub H.
This dyh, you said it's generated by OY and HTY. Looks like the quotient is just OY, no?
No. Quotient
by H.
So think of the following example. Y is, say, spec maybe K of Y. Then, so X is spec K of X, Y, right? This cotangent bundle. And then, okay, so what is dy? It's algebra generated by two variables, by variable, well, global functions, global differential operators, is K of X of Y dy, and the relation is that Y dy is equal to 1. So now what happens if I take dyh? Well, that's going to be algebra generated by two variables, y and dyh, and the relation is going to be that the commutator, so this is 1, and here the commutator is going to be h, right? Yes, so and I need to add formal. So
yeah, then the quotient is just by h looks like to be just K of Y, right?
No, because h times dy is not divisible by h in this ring.
It's just notation. Okay.
Okay, does it make sense?
Looks like
it's not a notation; it's a subalgebra here. But I take.
And why do you put double brackets? It seems that this subalgebra is just generated in single brackets over h.
Yes, I could define it over just polynomials in h.
I mean, it is contained there, right?
Yeah. Well, no, all
polynomial
power series in h. In fact, if you want to localize it over the cotangent bundle, then you really need the power series in h.
So I mean, when you say generated by OY and HCY, you mean also H completion?
Symbols, right? So it has two generators.
Yes.
H, Y, this symbol H dy, and subject to this relation.
I see. It is K of H. Right. K. It is a subalgebra over Taylor series.
Right.
I mean, in the general definition of dyh, you meant the subalgebra over Taylor series. I got it. So,
yes.
Yeah.
So that's what I wrote here.
You read it over K of H.
Maybe misunderstanding was that quotient by H means quotient by H multiplied by dyh, right?
Right. Right. Thank you very much. Okay. Now it makes sense. So that's called the risk construction. All I use here is the filtration on the algebra of differential operators. Okay. So so this way I get a canonical, well, very, well, say, canonical quantization of the cotangent bundle to any smooth variety. And in fact, there is even more canonical quantization of the same variety, the same Poisson structure. So you can sort of first generalize this. Well, let me put it not generalization, but a variant of this construction. Okay, so instead of differential operators from functions to functions, you can consider differential operators from a line bundle to itself, which is also form an algebra. So differential operators on Y, and for the line bundle, I want to take their canonical line bundle, right? So I can consider differential operators from sections of K to sections of K. So So of course, you can generalize it now even further. You can replace this this line bundle by any power of this line bundle, and in fact, even by a fractional power. In fact, you can take any power which is an element of this base ring R. For example, you can consider differential operators from square root of the canonical bundle to itself. Even though it's not a vector bundle, it's not a line bundle, differential operators from this fractional power is still defined. So you can construct this algebra, for example, first by choosing local trivializations and then glue. So you first do it for integral power and then observe that the resulting algebra is defined for any fractional power as well, provided again that 1/2 is in R. Okay, so and this gives me a quantization. So again, this is a filtered algebra. I can apply the risk construction, and I will refer to this the quantization that you obtain this way by as the canonical quantization. So canonical quantization of the cotangent bundle. So it's given not by the usual differential operators, by this twisted differential operators. It has one advantage that it has is that, well, as we know, the sheaf of differential operators is non-commutative. So a priori, there is a difference between left modulus over this algebra and right modulus. Nevertheless, the categories are equivalent. So, and the equivalence is given by the tensor product with the canonical bundle. So if you instead consider these twisted differential operators by the square root of the canonical bundle, then so this algebra is actually isomorphic to its opposite algebra. So the functor from left modulus to right modulus is the identity on the underlying vector spaces. And so this amounts to saying that this canonical quantization has the property, the following property. If I place here h by negative h, so if I consider the same algebra with different action of h, then it's isomorphic to OH canonical opposite. Okay, that's why it's sort of better than. Okay, so this is a basic example, and now questions. So what is what we want to do now? We want to understand. Well, we want to classify quantizations of given Poisson variety, Poisson scheme. So, for example, we want to see whether such a quantization exists, and well, what is the parameter space. And so, I will list some results in this direction. First result, which is due to de Wild, Leconte, and independently Fedosov. So this guys work in smooth manifolds, real manifolds, and in this algebraic setup that I consider the corresponding results are due to Bezrukavnikov and Kaledin. So they prove the following, that if the base ring is C, And so X is symplectic. In addition, they require that certain homology of the structure sheaf vanish in degrees I equal to 1 and 2. So what they proved is that the set of isomorphism classes of quantizations of X omega and bijection with elements in de Rham homology, second de Rham homology of X, well, tensored with power series. So power series with coefficients in this vector space. In particular, there is a preferred element here, 0, which corresponds to certain quantization X or X canonical or H canonical. This quantization has very nice properties. So what do I mean by saying that quantization is canonical? In particular, I mean that any automorphism of that this sheaf of algebras is equivariant with respect to everything that acts on this symplectic variety. So it's equivalent with respect to automorphism, symplectic automorphism of X and omega, right? So, for example, if my symplectic variety is the cotangent bundle, so then this canonical quantization coincides with the differential operators twisted by the square root of the canonical bundle. So the construction is of this canonical quantization is pretty simple, but the fact that this algebra carries this section is highly non-trivial. And in fact, as you're going to see, once you have this section, you can immediately globalize, almost immediately globalize the picture. Well, you can, starting with a cotangent bundle, you can construct quantization of every symplectic variety. So this is one result. So it's over complex numbers. Now there is another result which is also due to Mezrukamnikov and Kledin. So K here is a field of characteristic P, and for safety, I will assume that it's perfect. Maybe that's also greater than 2. And here I will assume that the symplectic form omega is actually exact. Well, that's not the most general case where the construction works, but still you need some at least local exactness, local Posarisky topology. And also I will assume vanishing of certain cohomology groups of the structure sheaf. So here I is 1, 2, or 3. And then again, so there is a they construct a canonical quantization, and together it's canonical in a sense that certain group, namely the group of automorphisms of symplectic variety X, with the property that phi upper star of eta minus eta. Well, it's not 0, but I require it to be exact. Right? So in particular, it means that omega is preserved under phi, but that's a stronger condition. And this group acts on this canonical quantization. Okay, so just a few words about how this construction works. Well, all these approaches. Well, there are many more important results on quantizations. For example, Kontsevich proved that every Poisson structure on the affine space can be quantized, and there is a generalization to other Poisson varieties over the field of complex numbers. But this is kind of maybe an irrelevant for my talk. So, so what is a basic idea?
Vadim,
Yes.
I think that Roma is asking a question. Can you have a look at the chat?
Okay. Well, so maybe I hope yes, but maybe let's discuss. So the question is whether this group acts on the quantization itself, or on the category of modules over this quantization, or only on the category of modules over this quantization. So so I hope that I'm what I said is correct, but maybe let's discuss it maybe later. Maybe Roma is right. So so basic idea. So what you do? Let's say for concreteness, basic idea of one. Okay. So well, first you do the local case. So my x is formal spectrum of power series in 2n variables. Okay, so I really think of this as a formal completion of the cotangent bundle to the affine space. And my omega is the standard symplectic form, which I prefer to write dyi h dxi. So let's call this this algebra A0, and now it has a quantization. Well, that's a special case of the construction that I explained about. Well, this cotangent bundle. So explicitly, I can take well, for OH, I can consider the following algebra, just the Weil algebra. So it's it has it's algebra which is kind of non-commutative power series with in well, 2n variables x1 xn, y1 yn, comma h, and let me also give a special name to this. So this is the Weil algebra. I call it A sub h. And the relation is that the commutator of xi and yj is equal to h times the Kronecker symbol ij, right? So that's agrees with this example. It's a fine a cotangent bundle to A1 that we discussed earlier. So this is obviously, this is by construction, it's a quantization of this A0. And now so locally, using the formal Darboux theorem, if you have now well, what you can try to do, you can so if you are given any symplectic variety, you can around every closed point you can pick coordinates such that in the formal neighborhood the symplectic form omega is given by this form, is the standard one. Again, this is the Darboux theorem. So you can identify the formal neighborhood of every point of the symplectic variety with this standard local module, and you can quantize it. And so now the problem is how you glue it. So in order to glue it, what you have to do, you have to kind of study what happens if you change these Darboux coordinates. So so you have to look at the automorphism group of this local module. So preserving this automorphism of this group of automorphism of this formal power series preserving omega, and you have to compare it with the group of automorphism of the quantization. Of course, there is a map from one group to the other. So if you have an automorphism of A sub H, you can reduce it mod H. It will automatically preserve the symplectic form. But and one can even show that this map is surjective. Now, if we were lucky, so this map, if this map had a splitting, if I add this arrow, then I could obviously glue this construction, right? I can glue, so basically locally define quantization by this formula, and this will not depend on the choice of Darboux coordinates, because this symplectic automorphism of the formal disk acts on this algebra. But unfortunately, this does not exist. So the idea is to study the kind of the kernel of this map, call it H, and well, so the basic idea is that so this group has a very large unipotent radical, and so if you mod it out by the unipotent radical, then the splitting exists. And so on the other hand, unipotent, you can take care of this unipotent radical by using this this assumption that higher cohomology, certain cohomology of the structure sheaf equal certain cohomology groups of the structure sheaf equal to 0, and so this finally allow you sort of to lift the canonical torsor on every symplectic variety under this group to a torsor under this group, which is which gives a quantization. That's kind of the basic strategy. So the main work is analyzing automorphism groups of this formal disk preserving omega and the automorphism group of the quantized local quantized structure. Okay.
May I ask you?
Yes.
What's the abstraction for this section?
Well, what do you mean? What is abstraction?
Can you say informally why there is no such lifting?
Why there is no section? I think so. In this group, you have kind of, for example, infinitesimal translations. Think of A0 as like really the functions on the formal disk. So I consider automorphisms of this formal disk. In particular, I can consider translations by infinitesimally small number, right? So that's kind of an example of the automorphism that I consider. So this has a large group of commutative group, and it turns out that if you pick, so this is a large commutative group, and you cannot lift this commutative subgroup to a commutative subgroup here. So you cannot leave them to automorphism, which actually commute here. That's, I think, the so maybe I so let me see if I no, sorry, I think what I'm saying is forget this. So
Yeah, that sounds strange.
yeah, so I think this Heisenberg extension does not really what I'm saying is not correct. Right. So okay. So but still, I claim that this extension does not split. Again, so maybe we can discuss it later.
Right, so,
That's really an abstraction, but it's a minor abstraction in the sense that again, if I model out this group by unipotent radical, then the extension really splits by unipotent radical of each. So very good. So now, so what do I want to do? It turns out, which is kind of the maybe idea now, which is attributed to in literature to Deligne, maybe Kancevich, and other people, maybe Greenfield, and well, there is a long list, is that instead of looking at quantizations of algebras, look at quantizations of the category of quasi-coherent sheaf on X. So then, of course, if I have quantization of an algebra, I can consider the category of modules over this algebra over ORH, and this, I think of this as a quantization of this category of quasi-coherent sheaf. But not every quantization of this category comes from a quantization of algebras, and it's so it happens that quantization of categories are easier to construct. The description of these quantizations is cleaner. On the other hand, so the relation between quantizations of algebras and categories can be also understood. So the idea is to split the problem of constructing quantization of algebras in two problems. First, constructing quantization of the category, and then passing, well, constructing a generator of the quantization of the category. So in particular, so if X is affine, then, well, every quantization of the category comes from quantization of an algebra. In a sense, these are the same thing, but, well, not quite. You'll see the difference. So the difference is in autoequivalences. Okay, so let me explain what I mean by quantization of a category. So digression on, say, just abelian categories. So I need to tell you, what does it mean to deform an abelian category? Okay, so let's go back to this first slide. So when I defined the notion of quantization of an algebra, so quantization of an algebra is a sheaf of flat algebras over the power series together with an isomorphism model of OH model H and the original. So we have to make sense of this for categories. So, okay. So let's try. Let's see how it works. So suppose I have A in a abelian category. over R. R is some commutative ring. And I will assume that my category has all direct sums and some compact generators. So then what I can do, so what does it mean that a category, abelian category over R? It means that home space in this abelian category between any two objects is an R module. For example, if my category, think of about the category of modules over some R algebra. That's a good example. So if I have such a category, R linear abelian category, then I can define, I can tensor any object of this abelian category by a module. So V is in A.
Excuse me, R is commutative here, right?
Commutative, right? And M is R module. Okay. So how I define this tensor product? Well, I will define it by universal property first. I will tell you what are morphisms from this object that's going to be a new object of A. And so morphisms from this to any W is home over R from M to R module home over A from V to W. Okay. Hope this makes sense. And now using this this condition that my category has arbitrary direct sums, you can construct that this functor is really representable. So this guy always exists. And again, if you the basic example, so how you prove it? You write M as the co-kernel of homomorphism of free modules. And for free modules, you just take the direct sum of several copies of V. Okay, so the proof is basically one line. Okay, and now I can, using this, I can tell you what it means for an object. So let's say V in A is flat over R if tensor this functor V tensor product over R, it's a functor from modules over R to A is exact. Okay, and that's part one. And part B, we say that A is R flat. The category is flat over R. If well, before I state you their definition, so here is a basic example. So so we know what it means for an associative algebra to be flat over R. So I want so if I have an algebra A which is flat over R, I want the category of modules over this algebra to be a flat category. So the question is whether you can characterize this in categorical terms, whether you can characterize a property of an algebra A to be flat over R just in terms of the category of modules over A. And the answer is the following. So A is R flat if A is generated by flat objects. Right? So
generated is an abelian category, yes.
Yeah. Very good.
There is some more intrinsic definition by Wendy and.
So everything that I explain in so this subsection on abelian categories is due to Wendy and Van der Berg. Vadim Vanderberg, right? I should have said this. So so
Leuven, I think her name is Leuven.
So it's enough for my purposes, but they are they work in larger generality. Okay, so and now so again, so my goal is to define what it means to have a deformation of an abelian category. So now we can talk about flat categories over the power series. And the last thing that I have to tell you is what is the base sheet, right? How you can take a category over the power series and modify it by each. So so definition for a homomorphism of rings and a category, abelian category A over R. So define the tensor product. And again, so the correct definition should have the property that if A is a category of modules over some associative algebra over R, then this tensor product should be the category of modules over the associative algebra A tensor with R prime over R. Right. So, and you want to define it in purely categorical terms. So here is what you do. You take just the category is the category of R prime modules in A. So what it means is that you look at M in sorry, I used notation V. V in A together with a R algebra homomorphism from R to endomorphism over A of V. Okay. So that must be R linear. So very good. And finally, now we can talk about quantizations. Well, first of all, deformations, flat deformations of A. So let A be a category, flat over R, a deformation over the power series is just a collection of categories, A0 equal to A, A1, AN. So these are flat over R of truncated polynomials, HN plus 1, flat. And the condition is that A n plus 1 modulo H n plus 1, which now makes sense. This is the tensor product is, well, so there is another piece of structure is an equivalence between this quotient and A sub n, which is linear over the appropriate truncated polynomial algebra. Okay? With this equivalence. Okay, so a fact which is proven by Vanderberg and Wendy is that
I'm sorry, Leuven is her last name.
What?
Wendy is her first name.
So
Leuven.
Yes. Fact. Let's see. Let me write it down. So then Berg and Loven is that if deformations of the category of modules over some associative algebra A is the same thing, well, model equivalences. Is the same thing as deformations of objects of A, modular isomorphisms. Okay, so once you have an affine variety, at least up to equivalence, there is no difference between deforming, say, quasi-coherent sheaves and just the underlying sheaf of objects. However, well, it's not quite true because so this is only isomorphism classes. But for example, you may have a deformation. You have inner automorphisms of deformation that they kind of define. These are non-trivial as automorphism of your quantization, but this automorphism induce an end functor of the category of modules, which is isomorphic to the identity functor, right? So inner automorphisms do not act on the category of modules. But also, I mean, deformations of a category form not a one category, but two categories. So you have morphisms between endomorphisms. So you have, for example, center acts as endomorphism of the identity functor, and so on. So there is a kind of difference, but there is no difference when you pass to underlying sets. Okay, so now so maybe I will explain how what you do here, why this is true. So if you have a category of modules of an associative algebra, and you have a deformation AN. So you have a deformation of this category. You want to produce a deformation of the algebra. What you do, you consider A as a free module over A. So this is an object of A0. And so it's projective. It's free, and therefore it's projective. And you show that a projective object can be lifted, admits a flat lifting. Well, even a projective admits a lift to let's say M to AN under this functor. And so you define AN to be endomorphisms of this lift, and you need to take the opposite. So then if you consider modules over this guy, you recover this algebra. So the reason why deformation of the category is the same as deformation of the algebra in this case is that you have projective generator. Okay, so now what is the main result? I'm ready to state it. Main result. The result is the following. So suppose I have a ring R, and I assume that it has one half in it. So 2 is invertible. And I have a symplectic variety, X over R. And I assume that my form omega is exact. Exact. And So then the category of quasi-coherent sheaves on X has a canonical quantization Well, what do I mean by a quantization? Well, I explained for you what is a quantization of what is a deformation of a category, but what does it have to do with the Poisson structure? Well, so the fact which is due to Lowen and van der Berg is that locally every deformation comes from deformation of an algebra. So it makes sense to say that this deformation of the category is compatible with the Poisson structure. So let's say denote this quantization by Popoff X canonical. And again, the basic property of this is that it has the word canonical here in particular, that everything that preserves this structure acts on this category. So I will tell you precisely what the group that acts here. So I consider all automorphisms pairs phi, comma s, where s is a function on x and phi is an automorphism of x, with the following property that phi upper star of eta minus eta is not zero, but it's differential of s. Okay, so I consider all automorphisms that translate this one form by an exact form. And this group, you can easily, well, construct a group structure here, right? So you want to compose automorphisms and figure out what you need to do with these functions to make this condition satisfied. So that's a group, and it acts here. So it acts by autoequivalences. That's the main statement. And in the remaining few minutes, I want to sort of tell you what the idea of the proof is. Okay, so you as in Bezukhovnikov and Kaledin story, and well, Fedosov, so you first do it locally. So you construct, you consider local module. So you take just power series in 2n variables. And here you do have a quantization, so it has a map to y, which is going to be a formal spectrum, another formal disk. It's a formal spectrum of these guys. And now, so here I have the, so my claim is that it's enough to construct a global quantization. It's enough to construct an action of group G, which is again the group of all pairs phi in automorphism of X, and S is a function such that phi upper star eta minus eta is equal to ds, and eta here is sum of xi dy on the category of modules over the quantization. I already have this this notation A sub h. So this is a completed Weyl algebra in generated by xi, yj, and the commutator is equal to h. So okay, so that's kind of the main work is here, constructing this section. And so what you do, so I will explain it. So here is what you, so the main idea is to look at certain elements in this group, which are called transversal. So so let's say that phi in X, its endomorphism of X, is transversal if the following condition is satisfied. So we can consider the graph of phi. It's a closed subvariety of X times X, and it maps to Y times Y. And the condition is that this composition is an isomorphism. So this graph of phi is transversal to the fibers of this Lagrangian fibration. And so now, so for example, the identity automorphism is not transversal, but the automorphism that interchanges x, I, and y, I, is transversal. So, and well, so one can check that every automorphism is composition of transversal. So you sort of, you construct action of symplectic automorphisms which are transversal. So given phi and s.
Excuse me, is it now about power series and then variables?
Yes.
Not any affine, right?
It's more than, it's, yes, X is just the formal disk as well. Okay, so I think of this kind of X as a formal completion of the cotangent space to the affine line, and Y is a affine space, and Y is the completion of the affine space. It's a local, kind of very local module of everything. So and you sort of reduce everything to this local module using a version of the Darboux lemma. But again, so the main point here is constructing the action of this group G on this category. So this group G does not act on algebra itself. It acts only on the category. And so given an element, well, we want to construct its action on the category of AH module. So define its action on modules over A sub H. Well, how you define this action? So an action, well, an underfunctor of this category is given by a bimodule, right? So so we want a bimodule M phi sub s over A sub h, with the property that if you mod it out this by h, then you get the bimodule corresponding to phi, which is a structure sheaf of gamma phi. And you see this gamma, the structure sheaf functions on the graph of phi. Is the graph of phi is identified by this projection with y times y. So in particular, functions on this graph is a free module over functions on y times y. it follows that this kind of quantization of this structure sheaf should be also a free module over functions on Y tensor with Lorentz with power series in H. So, and this suggests that this should be easier to define this. So what you do, you just take the free module of rank 1 and you introduce an action of this value algebra, which is kind of action of the differential operators, asymptotic differential operators, by adding this symbol e to the s over h. So I recall that s is phi upper star of eta minus eta, and you take power series in each. Okay. So what do I mean here? So I need to tell you why this is a module, how h sub h.
Sorry, maybe ds, right?
No, how this acts here. So you can think of this geometrically as a d module on y.
No, I'm asking the condition. I mean, eta is a one form, right?
Yes, thank you very much. Thank you. So so I want to construct a d module on asymptotic d module on y times y. And for this d module, I just take the trivial line bundle, and the connection is dictated by this function s. So what I mean here is that xi, so yi act here just by multiplying by functions, and xi act as follows. So xi multiplied by, so if you want to act by xi on f times s over h, so what you do, you differentiate this expression with respect to d over dy. So so this is by definition h d over dy I of f plus ds over dy I times f, and you multiply this by exponential of s over h. This is just a symbol. So you apply the Leibniz rule. So again, so for every, not for every, but for at least for transversal element of my group of symplectic automorphisms of x, I constructed a bimodule. So I constructed an endofunctor of my category. That's not enough. So you also have to explain why. Well, not you have to construct a isomorphism between the composition of two functors corresponding to phi and s and phi prime s prime, and the functor corresponding to the product of these elements. You have to really show that this is a group action. And but well, I think I have to stop here. Thank you very much.
Any more questions about this detailed talk?
May I ask a question? May I ask a question? Do we have still time or not?
Sure. We're not in a hurry.
So you said you define it for transversal, then you should check that the composition works okay, but you should also, I don't know, I mean, it's some generators. You have some relations between these generators, right? When you define the whole group.
Yes. So
You should check. You should know these relations, right?
no, you don't want to write down. So you argue that that just it suffices to given an action of this group, of the whole group, it suffices to construct an action of transversal elements and the composition data for only for transversal ones. So the composition of transversal need not be transversal. So all three must be transversal.
Right.
So for some other formal reasons, so it's once you have this this datum for only for transversal one, it extends to all.
You mean by formal, you means you really use this formal argument that everything are power series in H?
Yes.
I see. Okay. All right. Thank you.
Any more questions? If no, let's thank Vadim once again. Thank you for everybody who gave talks and who attended the workshop. It was nice to see you all.